Hello dear learners, in this lecture we will try to understand the very basics of magnetospheric physics by solving some numerical problems. So, the first question is based on the calculation of beta value, which is a characteristic feature which determines the nature of plasma. So, beta parameter, we have talked about the beta parameter while we were discussing the solar wind and how solar wind is a high beta plasma. So, we are looking at solar wind at 1 astronomical unit, which is the distance between sun and earth. Now, we are given plasma, question 1, the concentration of plasma is given to be N is equals to 7 centimeter minus 3. That means there are 7 particles per cc, okay, and the temperature is given to be 1.5 10 to the power of 5 Kelvin, and the magnetic field is 5 nano Tesla, right. Now, what we have to calculate is number 1, thermal pressure, B, magnetic pressure, and C, the value of beta itself. The idea of thermal pressure is the force per unit area because of the collisions the particles will do on the walls. Let us say imagine a volume, and then if it is having some particles, the momentum transfer between the collisions gives the idea of pressure. The magnetic pressure is because by the virtue of the magnetic field, and thermal pressure can be assumed to be purely a function of the temperature and the number density, of course. And beta is a ratio of these two pressures which determines which properties are going to be manifesting dominantly, either the magnetic properties or the thermal properties, right. So, first we will calculate the thermal pressure. Part A is thermal pressure. So, we assume the temperature of electrons to be equal to temperature of ions, and we say that this is equal to the temperature that we are going to use in the calculations. So, PTH thermal pressure is equals to 2 N kBT. How did I get this factor of 2? We have talked about it. We can use N kB TE plus TI. We say that TE is equals to TI, then say it is equals to T. So, that is one, we get an additional factor of 2. So, because of the collisions, if thermal equilibrium is established, we can say that electron temperature and ion temperature will be equal. But if you do not give the plasma that opportunity or the gas that particular opportunity, either you are talking about a gas which is diffused or collisions are not possible, in that case electron temperature and ion temperature can be maintained separately and independently. So, in this expression we will just substitute what we know, 2 into 7 10 to the power of 6 particles, because I have converted per centimeter cube to per meter cube into 1.38 10 to the power of minus 23. The value of Kb, Boltzmann's constant, and the temperature is 1.5 10 to the power of 5. So, do this calculation, you will get it to be equal to 2 into 1.450 10 to the power of minus 11, or approximately equal to 2.90 10 to the power of minus 11 Pascal, or 29.0 pico Pascal. What is this? This is the thermal pressure. So, this is the pressure that the this weak plasma is exerting because of its temperature. Right. Now, what is important for you to observe, the calculation is very simple, but it is telling that the pressure is so small. Now, ultimately, the value of beta becomes highly relevant when you are trying to understand the magnetospheric standoff, or the distance up to which, or the distance of the bow shock from the surface. So many things, right? Now, let us calculate the magnetic pressure. Then we will see whether this is small or not. Okay, and then we have the magnetic pressure. Magnetic pressure PB is equals to B square by 2 mu naught. This is also a formula that we know very well. So, B square by 2 mu naught. So, we use the magnetic field, the frozen end magnetic field, 5 10 to the power of minus 9 Tesla square divided by 2 into 4 pi 10 to the power of minus 7. I am just using the standard value of mu naught. Most of the values that I have directly used, maybe sometimes I have just skipped telling what I am using, but looking at the flow, you should be easily be able to understand what I am doing. Right. So, if I do this calculation, I will get 9.95 10 to the power of minus 12 Pascal. If I rewrite it, this can be equal to, in terms of picopascals, it will be 9.95 picopascal. So, just trying to make a conclusion here. So, the thermal pressure is 29.0 picopascal, and the magnetic pressure is 9.95 picopascal. Right. Now, you clearly see that the thermal pressure is at least 3 times in comparison to the magnetic pressure. Now, part C is the calculation of beta, the beta parameter, which is PTH divided by PB. Now, if you have a very low magnetic pressure, the beta value will be very, very high. Right. So, this is 2.90 10 to the power of minus 11 divided by 9.95 10 to the power of minus 12, which is equals to 2.91. So, beta value is greater than 1. The solar wind is thermally dominated. We say that this solar wind is thermally Now, when we repeat this calculation in the magnetosphere, we will see a contrasting result. Okay. Now, let us look at this example. We have just been given the plasma parameters, the temperature and the magnetic field, and depending on the magnetic field strength, we are able to calculate the beta value, and this beta value is telling that the solar wind is thermally dominated. So, the magnetic pressure is at least 3 times smaller than the thermal pressure, and we ultimately say that the solar wind is a thermally dominated plasma or high beta plasma. So, that is something that we are recollecting, that we have used solar wind as a high beta plasma. Fine. Moving ahead, we have a very simple numerical which tells the validity of MHD, whether it is the conditions that we have used for MHD approximation. When do we say that they are valid or not? Okay. So, let us say we consider a magnetic flux tube at L is equals to 5 RE, this is the distance measure, and then the velocity is equals to 10 kilometers per second, okay, and sigma is 10 to the power of 7 SM inverse. Now, with this, calculate Rm, the magnetic Reynolds number, and conclude on the validity of magnetohydrodynamics approximation. Right. Now, the Rm, the magnetic Reynolds number, can be defined as a simple formula as this: mu naught sigma L V. So, which is basically a relation between diffusion processes and advection processes. So, we know that capital L is 5 RE, 5 times 6371 10 to the power of 3, which is 3.186 10 to the power of 7 meters. Then we have Rm, which is 4 pi 10 to the power of minus 7 into sigma is 10 to the power of 7 into L is 3.186 10 to the power of 7 into the velocity, which is 10 into 10 to the power of 3 meters per second. Right. To do that, then you will get the value of Rm as 4.00 10 to the power of 12. Now, these values are indicating an environment in the magnetospheric flux tubes, and by calculating the value of magnetic Reynolds number, we should be able to tell about the validity of the MHD approximation. Now, the magnetic Reynolds number in this case is clearly greater than 1, right. So, which is an ideal case for MHD validity. So, MHD is valid throughout the magnetosphere. Magnetic reconnection, which are actually violations of frozen in flux, requires anomalous resistivity or kinetic effects in thin current sheets, which are of the order of, let us say, 100 kilometers at the magnetopause and tile neutral sheets, where actually the magnetic Reynolds number approximately becomes equal to 1. Right. So, with this simple example, we are able to demonstrate how we can establish the validity of magnetohydrodynamics. And then we have another example, which is just a demonstration of the E cross B drift. Let us consider in the magnetosphere, the electric field is given as 1 millivolt per meter. What is this electric field? This is the dawn to dusk electric field, and the magnetic field is 300 nano Tesla. Let us say this is northward, and with these two values, calculate what is E cross B drift. Now, you see there are electric and magnetic fields. Now, a particle can experience, a charged particle moving with a velocity can experience E cross B drift. Okay. And find out the magnitude and then the direction of this E cross B drift. Subsequently, if the particles are under E cross B drift, so we can calculate what is the transit time across 10 RE. from the discussions of plasma physics, we know that the E cross B drift is independent of the charge. So, we can write the E cross B drift as V E cross B is equals to E cross B by B square, or we can simply write as E by B, which is 10 to the power of minus 3 volts per meter divided by 300 nanotesla, 300 10 to the power of minus 9, which will give 3.33 kilometers per second. Right. Now, let us talk about the direction. This is important. Let us fix a coordinate system. Let us say we have dawn and dusk electric field, right? We indicate the electric field in the positive y direction in GSM coordinates, and the magnetic field is told to be in the northward direction. So, we can say it is in the z cap direction. So, as a result of these two, the E cross B can be written as y cap cross z cap, which will be in the x cap direction, right. So, you're talking about this is the direction of the magnetic field, this to be, this is the direction of the electric field, and you are looking at resultant of these two in the x direction. This is about the direction. So, what is this? This can be in the sunward direction. The direction can be sunward. Reference could be sunward. So, that means that this x component is responsible for the magnetospheric convection. Magnetospheric convection. Right. Now, the transit time for 10 RE, S is equals to UT. So, at 10 RE, the time required is 10 times 6371 10 to the power of 6 divided by 3.33 10 to the power of 3, which will be approximately 1.91 10 to the power of 4 seconds, or 5.3 hours. Now, you see the dawn dusk electric field in combination with the magnetic field is producing the E cross B drift in the sunward direction, which is actually responsible for the magnetospheric convection, and the time that it takes for the transit is approximately equal to 5.3 hours. Now, what happens is during the storm time, this duration drastically reduces to, let's say, 1 hour. It reduces to 1 hour. Okay, fine. Now, this was an example based on the calculation of E cross B drift, which is a concept that we have learned in plasma physics, which is now being extended into the magnetosphere. Right. Now, we can attempt one more very important problem based on the gradient and curvature drifts. How do these two drifts contribute towards the formation of what is called as the ring current, etc. Let us imagine a 10 keV proton, 10 keV proton is approaching the earth, let us say at L is equals to 4, and the characterization of this gradient del B by B is 1 by Re, and we have the magnetic field as 200 nanotesla. We have the energy of the particle, which is going to experience the gradient drift and curvature drift. The scale of inhomogeneity or the scale of this gradient is given, and then we have the magnetic field itself, which is varying across this uh, direction in a particular way. Now, what we can do, what we may be asked to do is to calculate the gradient drift speed, then the direction of this gradient drift, and subsequently the drift period. Okay. Now, for solution, we should start with calculating what is the velocity of the particle. So, let us say the kinetic energy of the particle is half. We are talking about protons, mp v square, v perpendicular square can give us the v perpendicular written as 2 ke by mp. So, which is 2 times 10 keV. So, 10 into 10 to the power of 3 into 1.6 into 10 to the power of minus 19 divided by mass of proton 1.673 10 to the power of minus 27, which will come out as 1.384 10 to the power of 6 meters per second. This is just, we have just calculated the velocity of the particle. From plasma physics, the gradient drift velocity has a formula which is mp v perpendicular square divided by 2 eb times del b over b. Okay, so we will get, by substituting what we know, because mp v perpendicular square divided by 2 eb times 1 by re from here, right. So, we can calculate the v del b as substituting everything. So, mass of proton 1.673 10 to the power of minus 27, v perpendicular 1.384 10 to the power of 6 square divided by 2, charge of 1.6 10 to the power of minus 19 coulombs. Magnetic field is given to be 200 10 to the power of minus 9 Tesla into Re 6371 into 10 to the power of 3. Substituting all that and doing this calculation, we get V del B is equals to 7.84 10 to the power of 6 meters per second. Now, you look at this, whatever that is being asked is fairly simple, except that you should be able to write down, understand what is given, and then make suitable substitution into the formula. Now, if you don't remember this formula, you cannot do this problem. This problem is entirely based on a simple formula which we have derived while we are discussing plasma physics, right. So, this is just a typical example on how or which type of problems may be asked in your examination, right. So, now we have the gradient drift speed. Now, this velocity is relativistic for a 10 keV proton. We can find out the direction of this gradient drift velocity. So, when we take the magnetic field to be northward and the gradient to be pointing eastward, so we have to think of this system in which the magnetic field is like this. So, as we are approaching here, the magnetic field's direction is something like this, and then as we are moving towards the earth, the magnetic field is increasingly becoming stronger. So, there is a gradient in this direction which is exactly perpendicular to the direction of the magnetic field itself. Now, if you take this and then you think how these two perpendicular components will make the particle move or will decide the direction of this movement, we can apply a simple law and then say that particles with a positive charge, which is q greater than 0, which are basically the protons, will follow one path, one direction, and exactly opposite to that, particles with a negative charge will move. So, protons will drift westwards, as in this is Earth is rotating from west to east in this direction. So, this being the reference here is the sun. So, that becomes the side behind the drawing becomes the dawn, and this side becomes the dusk. So, applying the thumb rule, you can figure out very easily how the protons will move westwards and how the electrons will move eastwards, right. Now, this separation is what actually leads to the formation of the ring current, which is the most important thing when we are discussing the space weather influence on the Earth, right. Subsequently, we can also calculate the drift period. Drift periods, let us say C is equals to 2 pi L RE in terms of the L value. So, we can say 2 pi times 4 is the value that we are given with 6.371 10 to the power of 6 meters, which is 1.6 10 to the power of 8 meters. So, time is C by V del B. If you substitute these values, you can easily calculate how much time it takes for the drift. So, we can see that the drift period scales inversely with the magnitude of the E cross B drift velocity, right. So, I believe these problems, these numerical problems can help you understand the concept at a much deeper level. So, try to practice more problems based out of any book and try to relate the concepts which are asked in the problem to the topics that we have discussed in the class. So, with this I close this lecture. Thank you.